Alright guys, so we're looking into 3.9 part 2. In our previous video, we looked at finding the derivatives of exponential functions, things of e to the x or possibly a to the x with a different base a than our e. In this video, we're going to be looking specifically at the derivatives of logarithmic functions. And so our goals are to be able to find the derivatives of natural logs and things of ln of u, and then also finding the derivative of log with a base a of u and those types of functions as well. And so we're going to start some things off by looking into our proof for the derivative of the natural log of u. I don't like always just giving everything to you. I want to make sure that we're kind of showing where everything comes from as well too. And so we're going to go over the proof for ln of u's derivative formula, and then I will hand over the derivative for the natural log of a as well. So let's take a look here real quick. So let's say, for instance, we are dealing with the function y equals the natural log of x, okay? And so we know by our inverse relationship, what we know about our identities for log functions, the inverse relationship tells us that e to the y is equal to x, because e and natural log are inverse functions, and that's kind of where we get from, all right? So e to the y is equal to x. If you're not really comfortable with that, make sure you kind of take a step back and look into our log identities and that we've been talking about in the past. So we have our inverse function and its relationship right there. So now we want to go ahead and find out, just like we've done in the past with our proofs, we want to implicitly differentiate both sides. So we're kind of, wherever we see that y, we're taking into account the dy dx in there as well. So if you remember correctly from the previous video, the derivative for e to the y is just going to be e to the y. It's going to be the exact same thing. We did that proof in the last video. And so if that is the case, the derivative of e to the y is e to the y. But because we are implicitly differentiating, we have to differentiate what's in that exponent as well. And because y is in the exponent, we need to implicitly differentiate it. Well, y is just 1. But don't forget, you have dy dx hanging in there as well. And then if you take the derivative of the right-hand side, well, that is just going to be 1, because the derivative of x is just 1. And so this is what it looks like when we implicitly differentiate. And so to solve for dy dx, we can divide by e to the y on both sides, and we get 1 over e to the y. Well, if you remember correctly, we just said above that e to the y is equal to x. So this is really the same thing as 1 over x. And why is that important? Well, because this answer that I'm highlighting in green has to do with y being the variable in there. But dy dx is the derivative of y with respects to x. This is with respects to y here. So I need it with respects to x. And so that's when I make that change. The derivative of the natural log of x is really just 1 over x. And so that's kind of the proof, and that leads us into what the formula actually is. If I want to find the derivative of the natural log of some u, all right, whatever that function is, x squared, x cubed, square root of x squared plus 3, whatever it is just the 1 over whatever that u is multiplied by that u function's derivative, okay? So whatever that u is, if it's x squared or whatever the case may be, take the derivative of that inside and multiply it by 1 over u specifically, okay? And so that's going to kind of lead us into a couple of examples that we're dealing with. We're gonna go pretty basic to start some things off for this particular example here. So let's take a look at one in which it's not too crazy that we are dealing with. So let's look at taking the derivative for an example. It'll draw There we go. The derivative, for example, of let's see here, y equals the natural log of 10 over x. Okay, so this is what we're going to look into, for this particular example. So we're looking into the example here. Sorry guys, I'm having some issues with my iPad right now. So we're looking into this example. So we went from the natural log. Well, we know that it's going to be 1 over u being multiplied. So let's kind of highlight what u is to start off with. U is going to be what's inside of that natural log function there. So we can say that u is going to be 10 over x, right? And this is going to end up being 1 over u, but we'll get there in just a second. If I want to find out what du dx is, let's kind of take this one step further, and let's make u 10 times x to the negative 1. All right, why? Because it's going to be a little bit easier to find the derivative of 10 times x to the negative 1. So when I find the derivative, it's just our power rule. Negative 1 times 10 becomes negative 10, and then subtracting 1 becomes negative 2 for our exponent. So if you want, you can keep it as negative 10 over x squared. So to find our particular, our u function, we want 1 over u multiplied by du dx, which we just found to be negative 10 over x squared. Well, 1 over 10 over x is really just x over 10. So let's flip this and make this x over 10, and then multiply that by negative 10 over x squared. X's will cancel, one of the x's will cancel there, the 10 will cancel, the 10 will cancel, and then we get negative 1 over x as a final answer for this particular derivative here. Okay, so this is a good little insight into what we're kind of looking at for our problems in regards to our natural log. But one thing I want to look into before we leave this problem is just keep in mind, we have to make sure that x still fits the domain. So let's make sure that we say that x does in fact become greater than 0. Because remember, you can't have negative inside of that natural log. And then in this case, you can't have 0 in the denominator. And so we have to make sure that we fit kind of both of those circumstances there. As we wrap up this video, we want to look into the formula for our log with a base a. That was our second part of the goal. And so when we're finding the derivative of log base a of u, we have just kind of an easy formula, but we also have a stipulation. As long as a is greater than 0 and a does not equal 1 in this particular example, because we all know what happens to the natural logs of 1, we have the derivative of log base a of the function is equal to 1 over whatever that u is times the natural log of the base multiplied by the derivative of that u. Okay, so here is our formula rule. So once again, we can go into the exact same concept of proving this, but I'm gonna forego that for now and just kind of give us the formula for finding the derivative of the function that looks as such. So let's take a look real quick of utilizing one that might be a little bit more of a challenge because we're going to have to use a chain rule in it. So our last example of the day is going to look into finding dy dx of the function y equals log with a base a of a sine to the sine x. And this will kind of help us also look into some recap of our previous log identities and log rules that we've dealt with in pre-calculus and trigonometry. So let's find the derivative. So first and foremost, we know it's going to be 1 over u, which is, in this case, let me highlight u. U is going to be this entire a to the sine x. So this is all going to be u in this example. So let's make that a note. So let's make that a note. U is going to equal a to the sine x. So we know when we're dealing with our formula, we're going to have 1 over, so the derivative is going to be 1 over a to the sine x, and then we're multiplying that by the natural log of whatever that base is. Well, the base in this case is pretty simple. We're just keeping it as that variable a. And so we just got to multiply it by the derivative of whatever u is. Well, u is a to the sine x. So I need to find what du dx is in fact going to be. So think about it for a sec. We need to multiply it using our chain rule. So we have kind of a interesting situation that we're dealing with. So we have a to the sine x, finding its derivative. We know a to the sine x, we have that natural log of a being multiplied by the original a to the sine x. So we're going to be looking at a to the sine x being multiplied by the natural log of a. And then we need to multiply that by the derivative of sine. So we have our entire thing, and then we need to multiply it by that kind of that chain rule. It's that sub u that's inside of a to the sine x. And so we need to multiply that by the derivative of sine, which is going to be cosine of x. And so when this is all said and done, here is our derivative of a to the sine x. Once again, this part right here takes care of a to some x, right? And then we multiply it by u, the derivative of u, which in this case was sine of x, and multiply it by cosine of x. And so, kind of continuing to move it down here, we now multiply all of this by a to the sine x, multiplied by the natural log of a, cosine of x. Well, take a look what happens here when you multiply all these out. We're going to multiply a to the sine x will cancel with a to the sine x. The natural log of a will cancel with the natural log of a. And all we are going to be left with is cosine of x. And we can always kind of just double check and make sure that fits, because it does end up in terms of with respects to x, the derivative of y with respects to x in this example here. All right, guys, I want to get one for example, and I'll give you the answer as well, too, to make sure that you guys are all on the same page with this one in particular. So what I want you guys to do is give this one a shot. Find dy dx. In this case, you're going to look at example 1. Is going to be, let's see here, let's do y equals the natural log, I'm sorry, hold on, I'm writing this down wrong, x times the natural log of x minus x. Your answer for this one that you can double check is going to be the natural log of x. And then the second one that I want you guys to give a shot is y equals the log with a base 5 of the square root of x. And your answer for this one is going to be 1 over 2x times the natural log of 5. And there's a little restriction there that just makes sure that x is going to be greater than 0, so we don't get 0 in that denominator. All right, so we've got our answer here. Whoops. We have our answer here, natural log of x, and then our 1 over 2x to the natural log of 5. So you can give those two a shot and make sure that you come up with the exact same result as well. All right, guys, that's going to do it for this video, and wrap up 3.9 for us.